In this Python code walkthrough, I am going to show you how to build these animations that I am showing you right now. I used these animations for a YouTube video I made about a week or so ago, demonstrating the normal distribution as well as its PDF, CDF, and PPF counterparts. I get a lot of questions at how I make these animations. I use the Manim library, or more specifically Manim Community Edition. This is a Python library that allows you to build beautiful mathematical animations using Python code. It was made by Grant Sanderson originally from 3Blue1 Brown, and it got forked to create the Community Edition of Manim. So there's a lot to share here. I think that this would be a good community service for the Manim community. I really would love more people to be interested in the library, because you can do some wonderful visualizations for not just data science but math in general. And I will make a point in future videos to do more Manim walkthroughs as well as short 3-minute videos on how to achieve certain tasks using Manim. A lot of them will be data science, machine learning oriented though. So let's go ahead and dive in and get started, and I will show you how to build these animations. All right, let's dive right in and get started. Grab your coffee because there's a lot of code to walk through. So I'm going to bring in Manim, all of its dependencies. I'm going to bring in the normal distribution from SciPy, and then I'm going to import the OS interface to help with running the command line from Python later. I declared this data right here. This is actually a sample. We're going to simply use it to calculate the mean and standard deviation for the normal distribution, nothing more for the purposes of this animation. So I'm going to collapse that. I'm going to declare this scene to be named the PDF to CDF to PPF scene. Instead of extending a scene, it's going to extend a moving camera scene from Manim. This allows me to zoom in and out and pan the frame around. This will be helpful when I start with the PDF and then I zoom it out. I call everything, all of the initialization is going to happen in the construct function. This is going to override the construct implemented in the scene. I have this argument right here, skip animation. So because there's so much going on in this sequence, I broke it up into sections. And this was just a parameter that allowed me to skip sections while I was helping with the development. You can use it as well if you want to only render certain parts of this scene. So a couple of different models I declared in advance. So these classes, I have the PDF plot, the CDF plot, and PPF plot. We'll go through each of these as they're used, but I will show the PDF plot initially. So when I initialize it, I'm going to essentially save to it the mean, the standard deviation, the lower and upper x of this normal distribution, which I'm going to set the range to be plus or minus 3 standard deviations from the mean. It's also going to contain the axes. So the x range is going to be plus or minus 3 standard deviations essentially. The y range is going to be between 0 as well all the way up to the means output function value, PDF value, and then I'm going to buffer it with just a little bit of 0.1 on top of it. And I'm going to divide that up into four ticks. And then I have a couple of configurations done on the X and Y axes to not include the numbers for the X, but to include the numbers for the Y. And then for the Y configuration, I'm going to limit to 2 decimal places. So I'm going to tuck this away. Oops, I didn't mean to tuck away that much. So we have our axes declared. The plot is going to be called on the axes. I'm going to pass it this function f, which we declared. So this is a simple Python lambda. So it's a shorthand function where it takes a given x value, it passes it to SciPy's normal distributions PDF, and it accepts that x value. It will also pass the mean and standard deviation that built this PDF. And then and one thing to point out here is this PDF plot class I declared extends a V group. This is a special type of class in Manim that essentially holds a group of vector objects. So vector group is really what it's short for. And you can do a lot of useful arrangements in Manim by putting several objects inside a V group. And then I'm just going to save the function, the axes, and plot to this class. I do have some helper functions we will use as well. So for a given x value, return the corresponding point. That is the input and output variable values for that given x value. And that's simply delegating to the axes C2P, passing the x value as well as the result of passing x to the PDF function. And the area range, so this will return a area under the curve that's shaded, and that shade's going to be blue, and I define it with an interval x start and x end. That delegates to the axes get area, passing the plot, the color, as well as the range of x values. So we'll come back to the CDF and PPF model later. As you can see, I've collapsed those, but I'm going to collapse them for now, and I will also collapse the PDF function, or the PDF class, sorry. I will calculate the mean and standard deviation off that data, like I said I would. I am going to declare this section, create PDF and CDF and zoom out. So this is just a way to help keep this very long sequence of animations organized and kind of break it up into stages. And notice that the skip animations, I set it to the skip animations argument I declared earlier. So this is a way I can blanket all of these scenes to be skipped and skip those animations as I'm iterating the work. And I don't have to render the whole entire scene. I only render that part of the scene I'm working on. So when I can set this to true in order to just skip all the animations save for that one scene that I am working with. I will declare my PDF model, so passing that PDF plot we were just looking at, the mean and standard deviation. And then I'm going to declare the CDF plot as well. So let's bring that in next. It really is very similar and follows the same pattern of the PDF, but you'll notice that it's using SciPy's CDF function, not PDF. And I changed the range. The range for the x is going to be the same, but I changed the y range to essentially be between 0 and 1. I had a little 0.1 at the top just so the S-shaped curve doesn't hug the top of the graph. And then I increment the tick marks by 0.25. And then I'm going to configure the y-axis to include the numbers as well as limit the number of decimal places to 2. So, that declares the axes. Then we call the plot on the axes to plot that S-shaped curve using that function. And then we'll add the axes in the plot. And we'll also save the function axes and plot inside this class instance so that we can refer to them easily later. And it also extends vgroup. So very similar pattern to what we did with the PDF. The x2p, just like we did with the PDF, this will recur for a given, it'll return the point on the screen for a given x value, input, as well as its output variable of the probability coming out of the CDF. So it delegates to the C2P function on the axes. I also have this function that plots the area all the way up to a given x value, which we saw in the video. And so this is something we will use quite a bit. I also have these two helper functions to get the vertical connecting line for a given x value all the way up to the curve, as well as the horizontal line from the y-axis all the way to the curve. So it allows me to trace a given point on the curve to the x-axis and y-axis. So that is the CDF. That is the CDF class. Oops, and I just collapsed everything. I didn't mean to do that. So that's the CDF class, or CDF plot class. And then I'm going to, and like I said, I declare those two models. And then I am going to declare the PPF plot for later and move it to the right side of the screen. But I'm not going to show it yet, but I am going to put it there for now. And then I'm going to take the PDF and CDF up here that we created, And because they are already organized as a vector group, I will put them in yet another vector group and nest them inside that new vector group. I will arrange them downwards, so it'll stack them nicely in a downward stack. And I'm going to scale them so that they fit the height of the Manim screen, and Manim has a height of 7 units by default. So that will compress those items down to 7 units in their height, and it will maintain the proportion of the width and height. Actually, I can't remember if it was 7 or 8. I think it might actually be 8 units, and I just made it 7 so it didn't hug the edge of the screen. Now the PDF, I'm going to add the PDF model to the scene. That'll include the axes, the plot, and everything. Now this is where extending the moving camera scene is useful. I am going to save the current state of the frame, and then I'm going to zoom in by a factor of 0.6, and then I'm going to move to the PDF model. So that effectively zooms in the camera by a factor of 0.6, and then I focus that camera on the PDF model. None of this is animated yet. I'm just getting things set up. And this is where I finally run the animation. I'm going to restore the frame and have it zoom back out. And as it zooms back out, we are going to see the CDF axes revealed as they fade in as we zoom out. And then we're going to wait for 1 second. So that is the end of that first section. Next up, we're going to draw an area between the PDF and CDF. We're also going to label both of them. So that's the name of this section. I'm going to create a value tracker here. So a value tracker in Manim is very useful because it allows you to redraw shapes and objects, and anything that depends on a certain value shifting and changing, it allows you to automatically update based on that value. So I'm going to initialize the X upper tracker. This is going to be a variable of the given X value I have selected in the PDF and CDF. And I'm going to initialize it so it starts on the far left side of the graph, which will essentially result in an area of 0 by going 3 standard deviations to the left. We're going to declare the area for the PDF, and I'm going to use what we call the always redraw function. So the always redraw function is going to be updated on every single frame, and this is where we utilize the value tracker. So as I shift and shade different areas of the PDF and then do lookups on the CDF, I'm always going to have the PDF always redraw that area based on whatever the value of the X upper tracker is. So I'll call the PDF model and then call that area range function we declared in it. It's going to shade the area from 3 standard deviations, the far left edge of the graph. That's effectively negative infinity, but that's the end of the x-axis range. So that's the far left edge. And then I'm going to go all the way up. I'm going to grab the area all the way up to the X upper tracker's value. You call the current value out of the value tracker, get value, and that will return the current value it is storing. So it's going to redraw this object on every single frame, this area object, so that we can see it updated between each frame, going from a lower bound X value all the way up to an upper bound X value. And I'm going to set the color currently to be blue. We'll draw the connecting dashed line between the PDF and CDF projecting the area. This is going to be a dashed line, and I'm doing some type hints in Python to kind of help the autocomplete as I was coding this. It's also going to be an always redraw. So this is the line, that little yellow dashed line that ties the PDF to the CDF on that given X upper tracker's value. And it kind of shows that neat little projection of capturing the area up to a PDF, but showing the value for that area on the CDF. And the start of that dashed line is going to be the PDF models given X value to point, and I'm just going to simply pass the given X value in the tracker. And the CDF model's X to P is going to do the same thing. It's going to return the point on that S curve for the given tracker's value. Now, because this tracker is always, can change between frame to frame, and Manim will interpolate and we'll see this in action shortly, we'll interpolate what the X value should be for a given duration of time to execute that animation. This will always redraw that connecting line accordingly, and I'm going to make that dashed line red. So we'll project the area to the CDF as X upper increases, the tracker increases, but we'll also show the area as a decimal. So we'll have that partial plot of the CDF that is going to reflect the plot all the way up to that X value. So when I build that S-shaped curve, I'm not building it all at once. I am projecting the area as I slide that PDF area, and I'm showing the capture area up to that point. So I'm only going to plot up to that given X value, which I have that CDF model do up here, which I just jumped to it. It's only going to plot that function only to the specified X value as the max. And this allows me to create that neat little animation of not building the entire S curve, but rather animating that S curve being built all the way from 0 to 1. So going back to where we were, so right here, I also will have an area label. It's always going to be updated as well. It's always going to be redrawn. I'm going to use a decimal number. So this is a nice little label where you simply pass it a floating point value, and it will take care of how many decimal places it should show in that given label for that decimal number. And I'm passing it the CDF model's probability value using its function, and I'm just passing the X upper tracker's value. And I'm going to scale that down by a factor of 0.8, so make it a little smaller. And then I'm going to set it next to the point on the CDF on that S curve for wherever that point is on the S curve. So I'm getting the X value from the tracker, and I'm looking up for that given X value on the CDF, what is the output variable value. And that will give me a point. And so this area label is always going to follow that point. And I'm going to put it on the right side, So we'll populate so finally we're going to execute the animation. We're going to fade in the area, the connecting line, the partial plot, as well as the area label. We're going to run the animation for 5 seconds by filling the whole PDF scene. So we're on that value tracker. We're going to call animate, and then we're going to call set value, and we're going to set it to the max of the range on that axis, which is going to be 3 standard deviations to the right. So mean plus 3 times standard deviation. That will bring me to the upper bound of the normal distribution, as well as the CDF and PDF. That will gradually interpolate in between each frame what the X value should be. And that's one of the neat things about Manim is it will execute the interpolation math for each frame for a given amount of time, which in this case is 5 seconds. And then all of those always redraw functions will update all of those objects pointed to that X upper tracker accordingly. So very cool. We're going to wait a second. It's always a good habit between each animation to put in a wait. And when you go and edit this video for narration later, you have nice little spaces to do freeze frames and so on, so you can hold a given frame while you narrate before you move on to the next step. And I've been using a video editor for that, which is a whole separate topic. We're just using this to produce the animations to put into the video editing software. And then for here, we're going to fade out the area connecting line CF partial plot, and the plot of the CDF model in the area label, because we're going to reset and get rid of those items so that we can look up specific values. So we're going to bump the PDF and CDF to the left edge. So we are going to scoot those over to the left side of the screen. If you recall earlier, we put the PDF and CDF in the left panel, which is just a V group holding those two items, and we arranged them down and we scaled them down to fit a height of 7 units, which again, I believe Manim's height is 8 units. Don't hold me to that. And so I move it to the edge, which means I'm going to put it to the left side of the screen. And there is a buffer argument to change how much buffer there is between the edge and this given object or group of objects. And this will give me some room to do some work on the right side and to create some other objects, such as the subtraction scene to calculate a given middle range area, which I'm going to show shortly. But before we even get to that, we're going to label both the PDF and CDF and flash that in, which is pretty simple to do. I just create a text object and just label the cumulative density function, probability density function, respectively. I scaled both of those down by a factor of 0.75, so I decreased their size a little bit. And I'm going to put each one next to the CDF model and the PDF model, respectively. I'm going to put it on the right side of that object. So these next two commands are very, very nice to use, because you can move an object relative to another object and say, okay, which side should it be on? In this case, I say put the labels on the right side of those objects. So I'll fade in those labels, because we only created them. We didn't actually fade them in or add them to the scene yet. We'll wait a second, and then we will fade them out. And then we'll wait another second. And that is the end of this section. Okay, so next up, we're going to show an area lookup from the PDF to CDF all the way up to x equals 70. So I'm going to create a label of just containing the number 70, scale it down by 0.8, and I'm going to put that on the x-axis of the PDF, where x equals 70. This is why I call the axes.c2p right here. So this is going to take the coordinates of 70, 0, and look that up on that given axis for the PDF, and that will return the point on the screen, not just the point on the axis. And I want it to be 0 because I want to be on the x-axis, where I want the y, the output variable, to be 0. And I'm going to put that label below that point. I'm going to reset the x upper tracker and set that value back to the left boundary of the axes. That's going to be 3 standard deviations to the left. I'm going to fade in that label that I just created. I'm going to add back the area and that connecting line. So when I add that, it's not going to animate them in, it's just going to throw them in immediately. And because the value tracker is on the far left position, you're not going to really see the area yet, because the area has an area of 0. And the connecting line will be visible though. And then we're going to animate the value tracker and set the value to 70. So it's going to, in 1 second, because that's the default time for a play of an animation, it's 1. I mean, I could set the runtime to a different value if I wanted to. But for now, I am going to just simply animate it and set the value to 70, and that will take 1 second. And that will update the connecting line in the area accordingly. And I'm going to label the area in the CDF, so I'm going to use the CDF model's function, pass the value 70, and that is going to return the area. I'm going to pass that to a decimal number label, format it to 3 decimal places, and I'm going to put that next to the connecting line at the top of it, and I will put it in the upper left. I'll make it upper left to the top of that connecting line. And then I'm going to get the center of that area, the center of that polygon. And so I'm going to call PDF model.axes coordinate to point. I'm going to pass the mean as well as what the y value is for that mean, and then subtract by 0.5. So what I'm doing here is I'm trying to get the center of that area mass, not just horizontally, but also vertically. There is a function in Manim called get center of mass that I've been told should help do this for me, but I still had some issues with it, and maybe I'm just not using it properly for my particular use case. That's something I will investigate later. Any learnings I do find, I will probably make a video for. And then I'm going to create a question mark inside a text label, and I'm going to move to the center of that area. So I will put that question mark in the center of that mass, and then I will fade it in. Next up, we are going to look at this horizontal line on the CDF, that little dashed red line. That's going to be an always redraw. I call the horizontal line on the CDF model, pass it the tracker value. That's always going to be updated based on whatever the value tracker's set at. And then I'm going to do a right animation to bring it into the scene. So it'll like do a little sketch animation to bring it in. We'll show the area lookup label for the CDF, then we're going to move it to the area. So we'll bring in that label on the CDF, but then we're going to wait. We're going to remove the area question instantly, and then we're going to animate that label being moved to the center of the area plot on the PDF. Let's move on to the next section where we show an area in the middle range lookup from the PDF to the CDF. So I'm going to wait a second, and then I'm going to break up the area into two pieces. This was a little tricky. So I needed to subtly break up the area into two areas. So from 65 to 70, and also have that left tail all the way up to 65. So I'm going to have this area 65 to 70. It's always going to be redrawn. It's going to be an area range from whatever is the upper bound of the tracker all the way up to 70. So this X upper tracker is actually acting as the lower here, and then it's going to have the upper range be 70. And then I'm going to add that area. And then so I'll move the area up to 70 to the right side of the screen. So I will take that area of up to 70, move it over to the right, to the top right corner of the screen. I'm going to put the area as well as its label together in a group, and then I'm going to call the copy function. This will do a deep copy, so that'll also copy the objects inside the group. And then I will call that the area 70 panel. I'm going to animate it, scale it down by a factor of 0.8, and then put it next to the left panel. And then I'm going to bump it to the upper right edge. So actually in this next to left panel might not have been necessary. I might have just left that in here, but because I think the to edge is going to override it and actually do its own thing. It's going to literally put that to the edge of the upper right side of the screen. Then I'm going to wait, and then I'm going to fade out that label, that CDF70 label, not the one we copied over, but the original one. And then I'm going to label 65 on the x-axis on the PDF. So I'm going to use math text, create the 65, scale it down by 0.8, so make it a little smaller. Then I'm going to put it next to the point on the axes of 65.0 on the PDF. So 65.0, that coordinate on the PDF is what we're putting it next to, or we're putting it below it. So again, we're using the coordinate to point function on the PDF model's axes to convert that 65.0 coordinate into a point on the screen. Now we're going to switch the area color to red, because we're now going to get the area we're subtracting, which is going to be the area up to 65, and subtract that from the area up to 70. So we will set the value to 65 on the tracker, and this animation will last for a minute, and then we'll also simultaneously fade in that label of x equals 65. We'll draw the horizontal connecting line on the CDF, and we'll also draw the question mark. So we'll bring in another question mark, put it next to that that area chunk, that middle range area, get the left side of it, and then put the question mark on the left of its edge. And I found I had to shift a little bit. Again, this is where I probably should have used the get center of mass function and try to work it out, but I just did some manual correction and just shifted it further to the left by a factor of 0.2. So the left is actually, this would bump it by 1 unit to the left, but if I multiply it by 0.2, that will only shift it by 0.2 units. And then I'll wait, and then I'm going to write the question mark, write that horizontal line on the CDF. Then I'm going to label that area for x is less than or equal to 65 in the CDF, so that will be a decimal number passing 65 to the CDF model's function. So that is what gets passed to SciPy and gives me the resulting area from the CDF. And I'm going to set it to 3 decimal places. Then I'm going to set it next to the top of that connecting line, again putting it on the upper left of the top of that connecting line. Then I'm going to wait a second, fade in that 65 label that we just created. And then I'm going to wait, remove that question mark immediately, fade out that horizontal line on the CDF, and then I'm going to animate moving that label to be next to that middle area between 65, 70. I found the best way to position it inside that asymmetrical area object was to get the left side of it and then put it to the left. And then we'll wait, and then we're going to wait for another second. Now we're going to take that area as well as its label, and we're going to put it in a vector group. I'm not going to copy the vector group this time. I'm only going to copy the area itself because I want to show the label CDF65, that given area, as the answer. So I don't want to remove the label. I kind of want to put some emphasis there and keep it there. But I'm going to put it in a vector group, and I'm going to copy the area, and I'm going to declare a minus sign, scale it up by 4. So I'm going to blow it up by a factor of 4, make it bigger, and I'm going to put it next to that area 70 panel, but put it below it. I'm going to have a buffer of 0.5, so I'll pad it by 0.5 units. I'm going to remove that area. I don't need it anymore. Then I'm going to fade in that minus sign. Then I'm going to take that area 65 panel that I declared up here, containing that area I've copied, as well as the 65 label. Animate it, scale it down by 0.8, and I'm going to put it next to that minus sign, but I'm going to put it below the minus sign. And the aligned edge, this is a really helpful argument you can do in the next two function, is I'm going to align it to the left border of the area 70 panel. So it's going to left align essentially. And the left align is going to stop at whatever the left edge of the area 70 panel is. And I'm going to give that a buffer of 0.5. So I'll play that animation, and I'm going to wait for a second. Finally, I'm going to create an equal sign. I'm going to blow it up by a factor of 5, so increase it by a factor of 5. I'm going to have it match the width of the minus sign. So this was a little tricky. It was a little awkward taking some math text, but making it really large to show the subtraction operation between the area up to 70, subtracting the area up to 65, and what that equals. So I made the equal sign have the same width as the minus sign. It proportionally scales it down. And then I set it next to, I took the area 65 panel, the area 70 panel, and I put those both in a group just for the sake of this operation. So treated this as a single object. Put it next to that, but put it below. And this was my way of dealing with the asymmetry of those two objects, the area 65 and area 70 panels, because those partial areas were a little weird and they were aligned strangely. So I found putting them in a group together and kind of putting an imaginary box around them got the desired result I want. And then I could put this equal sign below them, and I gave it a buffer of 0.5, so 0.5 spacing. Then I label the area X between 65 and 70. So I take that, I create a decimal number of the area between 65 and 70. That is going to have 3 decimal places. And I move it to the middle of that, area that's left over, that middle area between 65 and 70. And I found I had to manually shift it down by half a step, just to make it look a little bit better. Again, I really need to explore the get center of mass function a bit more. I fade in that label 6570. I fade out that connecting line. I wait. And then, and then I'm going to move that area 65 through 70. I'm going to put that to the right side, put that below the equal sign. So I group up that label and that area. I do a deep copy of it. And then I'm going to fade in the equal sign. Then I'm going to take that panel I just declared of those two, of the label and the area. And then I'm going to animate it, scale it down by a factor of 0.8, so make it a little smaller. Put it next to, I put a whole group containing the area 65 panel, the area 70 panel, and the equal sign. So I put a big box around that essentially by putting in a V group, and then put the area 65, 70 panel below that entire group of objects. I put it below, and I put a buffer of 0.5, and then I shifted it to the edge. I shifted it to the right, so that the tail, so that the right side would kind of align to, so the center area, I wanted its right side to kind of line up to the right side of the area up to 70, and I achieved that by doing the to edge to the right side. And then I wait for another second. Now that that's all done, we can do some cleanup. I'm going to group up all of these elements and fade them all out as a single group. So that includes the area panels, the equal sign, the minus sign. So I just do one massive cleanup to leave only the PDF and CDF themselves and get rid of everything else. Because what we're going to do next is we're going to take the CDF and do that animation to turn it into the PPF, the probability point function. So I am first going to copy the CDF model axes, and then I'm going to do a couple of rotations. So first I'm going to rotate it by 180 degrees along the x-axis, and then I am going to rotate it by 90 degrees by default on the, I believe it's the y-axis, if I recall correctly. I believe it's the y-axis. So actually it rotates, it rotates along the out-axis. So when you do a rotation, it's actually going to rotate relative to straight on the screen, so towards the out direction. And then I'm going to do something called a fade transform. So I'm going to take that axes I just copied, and then make it become the axes on the probability point function model. The fade transform, when you have two objects that don't seem to transform from one to the other as well, it's a good transformation to resort to, where it just basically does a fade illusion to make it look like the transformation is happening, but it's really fading from one to the other. And then I'm going to bring in the CDF plot, and copy it. I'm going to send it through the same rotation. So I'm going to rotate it 180 degrees along the x-axis. Then I'm going to rotate it 90 degrees along the out-axis. And then I'm going to animate it to become the plot for the PPF function. Now that's not a terribly hard thing to transition towards, because they're both S-shaped at this point. So there's a little bit of shearing and stuff, or stretch that happened between the CDF and the PPF, or just a little bit of transformation, but not tons. And then finally, I do a lookup for a given PPF. So I'm going to label the probability point function really quickly. I'm going to rotate that text by 90 degrees, scale it down by 0.75, and just put it on the left side of the PPF model. I'm going to wait, fade in that label, wait again, then fade it out. I'm going to set the area color to be blue again. I'm going to reset the X upper tracker to be on the left side of the axis, all the way at the edge, or the start of the range, which is going to be 3 standard deviations to the left. I'm going to get the area up to 75 as well. Numerically, I'm not actually doing the geometric area yet, but I am going to get the area for, or sorry, let me rephrase. I'm going to retrieve the X value that gives me an area of 0.75, and that's what's going to be saved right here. I call the PPF models function, which goes to SciPy. Actually, let me show you that, because we did not look at the PPF plot class. So it has the axes of 0.001 to 0.99. Now, the reason why I can't just do 0 through 1 is because that S-shaped curve will forever approach infinity but never reach infinity, or reaches. It's wrapped around those two asymptotes, and it will cause some undesired behavior by having 0 and 1 included in the range. So you just pad it just a little bit so it never includes 0 and 1, because the S-shaped curve will never touch those values. Then we're going to calculate, for the Y range, it's going to just go from -3 standard deviations all the way to up 3 standard deviations. The standard deviation itself is going to be the tick mark units. And the length of, and then we're just going to have the length of this graph before. And we'll also do some further configurations to the x-axis, only including 0, 0.25, 0.5, 0.75, and 1. Those are the only numbers we will see on that axis. We'll make the plot orange. It's going to use this function up here, which is, again, it's using SciPy's PPF function. I pass the x value, the mean, and the standard deviation, and that's going to return the given x value for an area x, which this actually probably should be p to be more proper, but I'll just keep it there for now. And I will add the axes plot, the functions. I have this P2P function, which literally looks up for a given probability value. What does that return? What point does that return from the curve at that given p value, that given probability value, or what we were previously considering the x value? We can also have the same methods to return a vertical line and horizontal line. So going back down to where we were, we are going to look up the x value that gives me 75% of the area. And this area 75, this is going to be the shaded area under the PDF. It's always going to be redrawn. It's going to call the area range from -3 standard deviations all the way up to the given x value from the tracker. I'm going to wait, add that area immediately, which again that area should be non-existent at first, but the moment we start animating the X tracker going all the way up to whatever value gives me 75% of the area, which I got from SciPy. So if I said scikit-learn earlier, I apologize. I meant SciPy. And I'm going to set that value to X, up to that X value that gives me 75% of the area. I wait a moment, and then I'm going to label 0.75, put it in the middle of the shaded area, which I do with the C2P function right here again. I'm going to fade in that label of 0.75. And then I'm going to move the question mark to the x-axis. So I'll take that area question I made earlier, move it next to that x value that gives me 75% of the area, the y value being 0. So it's literally right on the axes. And I call that, using the C2P again, I put it below that point, and I give it a buffer of about 1.15. I write in that question mark. And then I am going to get the vertical and horizontal lines for the PPF and CDF, respectively. And this is what's going to allow me to trace the PPF and the CDF simultaneously. And I'll write them as simultaneously in the same animation. Wait a second. And then I'm going to draw the horizontal line which reveals the X values. So I call the PPF's a horizontal line, the CDF's a vertical line for that given X value that gives the area of 75. And then I write both of those lines simultaneously, and then that's going to reveal the X value. And I'll put in that label of what that X value is, that CD coming out of that CDF or PPF. I'll set it to 2 decimal places, scale it down by 0.8, and then I'm going to put it on the CDF model on the axes where the X value gives me 75% of the area. I'll also set the Y value to 0 because I want that point to be right on the axes. I'm going to put the label right below that and give it a buff of 0.15. So that's the CDF label. I'm going to do something similar with the PPF. I'm going to copy that label and then move it to the PPF model on its axes where the X value is 0, but the Y value, which really it's actually the probability is the input and the X value is the output. So X is actually the vertical axis here. And then I'm grabbing the point of 0 and whatever X value gives me 75% of the area. Put it to the left, and that's going to have a buff of 0.15. I write both those labels simultaneously, wait. And then I am going to fade out that question mark immediately and then animate that area label, that X value label immediately to where the question mark was. And then wait a second and we're done. So we have finished that enormous scene. There was a lot going on there. It took me quite a bit of time to write, but it was fun to do. It's fun to share with all of you, and I really hope that you learned some new things here. There are a lot of great Manim resources. It's a very, very nice, welcoming community, and I do encourage you, if this stuff interests you, to please give it some practice. What we finally do here is when I run this script, it's going to check if it's the main method. So this is my way of checking if I actually literally hit run on this file. And if I did, then it's going to execute this command. So it's going to execute this command with Manim to execute this Python file and render the scene accordingly. And you'll see that I just set it. This sets it to low quality, whereas if I did K, that is 4K quality, or H is high quality. I'm going to suppress warnings. I'm going to have it automatically play immediately. I'm going to disable caching. And I just understand that disable caching does improve performance, doesn't take up as much storage space. The output file is going to be the PDF to CDF to PPF scene.mp4. The input file, which is this file we're walking through right now, I called it scratchpad.py. And then finally, the scene that we are rendering, that's the class name that we are rendering. It's the PDF to CDF to PPF scene, which if you go all the way to the top of the file, that is the name of the class right here. So folks, I hope you got a lot out of this walkthrough. The code is on GitHub. You can see it in the description below. And feel free to comment. And if you have any suggestions on other things you would like to see, just let me know. And I will try to get to those suggestions as soon as I humanly can. All right, till next time, thank you.